Hello and welcome. If today has felt long or your thoughts have been moving faster than you'd like, you're in the right place. Tonight, there is nothing to remember, nothing to solve, and nowhere you need to go. This is a gentle journey designed to let your mind slow down while curiosity stays awake. We'll be drifting across Earth's oceans, the blue spaces covering most of our planet, moving gradually from familiar shores into calmer waters. The ocean is a world of steady rhythms. Waves rise and fall, currents circle the globe. Life moves to ancient patterns far older than human memory. As you listen, allow your breathing to settle into that same rhythm, slow and unforced. Each fact is meant to feel like a soft ripple, arriving then fading without urgency. Tonight's journey begins at the surface, where light dances and horizons stretch wide. From there, we'll sink gently downward, exploring hidden landscapes, strange creatures, and quiet forces shaping the earth. You don't need to picture everything clearly. Let the images come and go. So find a comfortable position. Let your shoulders relax. Let the day drift away. The ocean is always moving, and now we begin to gather slowly. Among Earth's oceans, the Pacific stands alone in its immensity. It is so vast that it covers more surface area than all of Earth's continents combined. Stretching from Asia to the Americas and from the Arctic to the Southern Ocean, the Pacific feels less like a single body of water and more like a world of its own. To cross it by ship takes weeks. To fly over it takes many hours. And still, most of what lies beneath its surface remains unexplored. The Pacific contains the deepest trenches, some of the most powerful storms, and thousands of islands scattered like quiet punctuation marks across its blue expanse. This size has consequences. Storm systems born in the Pacific can influence weather half a world away. Earthquakes along its edges can send waves racing toward distant shores. Entire ecosystems drift, migrate, and evolve within its currents, often isolated from one another by sheer distance. Despite this immensity, the Pacific appears calm from space, a smooth blue curve with no visible borders. That calm hides motion, depth, and complexity beyond easy comprehension. As we continue, this sense of scale deepens, because the Pacific's vastness hints at another realization. Size alone doesn't tell the full story. What truly matters is how much water the ocean holds compared to everything else on Earth. With that broader view in mind, the scale becomes easier to feel. More than 70% of Earth's surface is covered by ocean water. Land, which feels so solid and permanent beneath our feet, occupies less than a third of the planet's skin. Everything else is moving water, shifting light and unseen depth. From coastlines and beaches, it's easy to imagine the ocean as something that begins at the shore. But in reality, the shore is just a thin boundary. Beyond it stretches water that continues uninterrupted for thousands of miles, wrapping around the planet in every direction. If you could walk straight across Earth without stopping, most of that journey would be over ocean. This dominance affects more than geography. The ocean absorbs enormous amounts of heat from the sun, redistributing it through currents that regulate temperatures worldwide. It also shapes weather patterns, guiding storms, rainfall, and wind across continents. Even the oxygen we breathe is closely tied to life drifting near the ocean's surface. As this fact settles, the ocean begins to feel less like a feature and more like a foundation. And once you recognize just how much of Earth belongs to the sea, another quiet truth follows. Not all oceans are equal in size. One, in particular, stands apart in scale. Among Earth's oceans, the Pacific stands alone in its immensity. It is so vast that it covers more surface area than all of Earth's continents combined. Stretching from Asia to the Americas and from the Arctic to the Southern Ocean, the Pacific feels less like a single body of water and more like a world of its own. To cross it by ship takes weeks. To fly over it takes many hours. And still, most of what lies beneath its surface remains unexplored. The Pacific contains the deepest trenches, some of the most powerful storms, and thousands of islands scattered like quiet punctuation marks across its blue expanse. This size has consequences. Storm systems born in the Pacific can influence weather half a world away. Earthquakes along its edges can send waves racing toward distant shores. Entire ecosystems drift, migrate, and evolve within its currents, often isolated from one another by sheer distance. Despite this immensity, the Pacific appears calm from space, a smooth blue curve with no visible borders. That calm hides motion, depth, and complexity beyond easy comprehension. As we continue, this sense of scale deepens, because the Pacific's vastness hints at another realization. Size alone doesn't tell the full story. What truly matters is how much water the ocean holds compared to everything else on Earth. Nearly all of Earth's water lives in the ocean, about 97% of it to be precise. The lakes, rivers, glaciers, and clouds that feel so present in daily life together make up only a small fraction of the planet's total supply. The ocean is the true reservoir. This immense volume gives the sea a powerful role in stabilizing Earth's environment. Water absorbs heat slowly and releases it just as slowly. Because of this, the ocean acts like a thermal buffer, preventing extreme temperature swings that would otherwise make the planet hostile to life. Even freshwater systems depend on this vast saltwater store. Rain begins as ocean water lifted into the sky by heat. Rivers return that water back to the sea, completing a cycle that has repeated for billions of years. Every sip of fresh water is, in a quiet way, borrowed from the ocean. Thinking of the ocean as a container helps explain its influence. It is less like a landscape and more like an engine circulating energy, nutrients, and life across the globe. And yet, for all that water, the ocean is not still. Its power comes from movement, from slow, endless flows that link distant places. That movement carries us gently into the next idea, because the ocean doesn't just hold water, it moves it. Beneath the ocean's surface, water is always in motion. Vast currents flow like invisible rivers, looping through entire basins and connecting oceans across the planet. Scientists often describe this system as a global conveyor belt, slowly transporting heat, nutrients, and gases from one region to another. Warm water near the equator drifts toward the poles, carrying energy with it. Colder, denser water sinks and eventually travels back toward warmer regions, completing cycles that can take hundreds or even thousands of years. These movements help regulate Earth's climate, smoothing extremes and maintaining balance. Without these currents, some regions would freeze while others would overheat. Europe, for example, enjoys relatively mild winters because warm water from the Atlantic is carried northward. This heat transfer affects rainfall, wind patterns, and even the productivity of ecosystems. Although currents move constantly, they are rarely visible from above. Their presence is felt rather than seen. A change in temperature, a shift in weather, a difference in marine life. As this slow circulation continues beneath us, it leads naturally to a more familiar example. One current in particular demonstrates the ocean's quiet influence on human life. A warm river of water that shapes climates across an entire continent. The Gulf Stream is one of the most powerful and well-known ocean currents on Earth. It begins in the warm waters of the Gulf of Mexico and flows northward along the eastern coast of North America before crossing the Atlantic toward Europe. Along the way, it carries enormous amounts of heat. This steady flow of warm water keeps regions far from the tropics much milder than they would otherwise be. Western Europe, for instance, enjoys temperate climates that would be impossible at its latitude without the Gulf Stream's influence. Winters are warmer, ports stay ice-free, and ecosystems flourish. For centuries, sailors relied on this current to speed their journeys across the Atlantic. Even today, it shapes weather patterns, guiding storms and influencing rainfall across multiple continents. Its presence is a reminder that the ocean's effects do not stop at the shoreline. Despite its power, the Gulf Stream moves quietly. There are no waves marking its path, no borders showing where it begins or ends, only gradual changes in temperature and life. As we drift onward, this idea expands, because currents like the Gulf Stream are not isolated. They are part of a larger system. And that system gives the ocean another vital role. It stores heat on a planetary scale. The ocean is Earth's greatest heat reservoir. It absorbs more than 90% of the excess heat trapped by greenhouse gases, quietly storing it beneath the surface. Without this capacity, Earth's atmosphere would warm far more quickly, creating conditions hostile to life. Water's ability to hold heat comes from its molecular structure. It takes time to warm and just as much time to cool. This property allows the ocean to act as a stabilizing force, buffering the planet against sudden changes in temperature. Days, seasons, and even centuries are softened by this slow exchange of energy. As heat moves through the ocean, it is redistributed by currents, spreading warmth across the globe. Some of it eventually returns to the atmosphere, influencing weather and climate patterns far from its original source. This hidden storage comes at a cost. As oceans warm, their chemistry changes. Ice melts, sea levels rise, ecosystems shift. The ocean's patience is immense, but not limitless. Still, in its quiet way, the sea continues to absorb and balance energy, performing work that no machine could replicate. And as we reflect on this invisible role, another realization follows naturally. The ocean is not just a moderator, it is essential. Without it, Earth would not resemble the world we know at all. Imagine Earth without its oceans. No clouds forming over open water. No rain cycling across the land. No currents moving heat from place to place. The planet would swing between extremes, scorching during the day and freezing at night, hostile to complex life. The ocean provides stability. It regulates temperature, supports the water cycle, and supplies oxygen through countless microscopic organisms drifting near the surface. More than half of the oxygen in the air comes from marine life, quietly photosynthesizing beneath the waves. Life itself began in the ocean. Long before plants rooted into soil or animals walked on land, simple organisms floated in seawater, protected from radiation and nourished by chemistry. Every living thing today carries that legacy. Beyond biology, the ocean shapes the chemistry of the atmosphere, absorbing carbon dioxide and moderating its buildup. It acts as both shield and partner to the land. Without the sea, Earth would be a dry, unstable world, more like Mars than the vibrant planet we inhabit. As this thought settles, it becomes clear that the ocean is not separate from us. It is woven into everything, and because it touches every continent, it also connects them, which brings us gently to the next idea. The ocean is the planet's greatest connector. Every continent on Earth touches the ocean. Even landlocked regions are shaped by it through weather, rivers, and climate patterns that originate far away at sea. The ocean is the planet's largest continuous feature, linking distant shores into a single system. For most of human history, the ocean was the primary highway between civilizations. Currents and winds guided trade routes, carried ideas, and connected cultures separated by vast distances. Long before satellites or airplanes, water linked the world. This connectivity exists beneath the surface as well. Marine species migrate across entire ocean basins. Nutrients cycle from deep waters to coastal ecosystems. Heat flows from one hemisphere to another. Nothing in the ocean exists in isolation for long. Even today, a change in one part of the sea can ripple outward, influencing weather, fisheries, and ecosystems thousands of miles away. The ocean does not respect borders drawn on maps. It moves freely, continuously. As this sense of connection deepens, the ocean begins to feel less like a place and more like a process, a living system in motion. And that motion never truly stops. Even when the sea looks calm, energy is moving through it, which leads us naturally to the next realization. The ocean is always active, even in stillness. At first glance, the ocean can seem perfectly still, a smooth surface reflecting the sky, barely disturbed by wind. But beneath that calm appearance, motion never ceases. Currents flow, tides rise and fall, and waves travel vast distances, even when they are too subtle to notice. Energy moves through the sea in layers. Surface waves ripple from distant storms. Slow currents carry water across entire basins. Deep below, cold, dense water creeps along the sea floor, completing cycles that began centuries earlier. This movement is constant, patient, and unstoppable. Even in the quietest moments, the ocean is alive with motion. Plankton drift, fish migrate, water molecules exchange heat and salt, maintaining delicate balances that sustain life. Stillness is an illusion created by scale. This perpetual movement is what makes the ocean so powerful. It shapes coastlines, regulates climate, and supports ecosystems across the planet. It also creates a sense of rhythm, a steady pulse that mirrors breathing itself. As we let that rhythm settle, the journey naturally deepens. Because once you accept that the ocean is always in motion, another question emerges softly. Where does all this movement lead when the water begins to sink and light slowly fades? As water continues to move, light begins to fade. Sunlight, so essential at the surface, cannot penetrate very far into the sea. In clear water, it reaches only about 200 meters down. Below that depth, brightness softens, colors drain away, and the ocean slowly darkens. This thin, sunlit layer is called the photic zone. It is where most familiar marine life lives. Fish, coral reefs, floating plankton, and drifting algae all depend on this narrow band of light. Photosynthesis happens here, powering much of the ocean's food web. But 200 meters is only a skin. Compared to the ocean's total depth, it is almost nothing. Most of the sea exists below this glowing surface layer, in places sunlight has never touched. As light weakens, reds disappear first, then oranges and yellows, until only blue remains. Eventually, even blue fades into darkness. Below this point, life must adapt in extraordinary ways. Understanding how little of the ocean receives sunlight changes perspective. The bright, familiar sea is only a doorway. Beyond it lies a vast, dim world waiting quietly below. And as we continue sinking, another realization follows gently. If sunlight reaches so little of the ocean, then most of the sea exists in permanent darkness. Below the sunlit surface, darkness becomes the ocean's natural state. More than 90% of the ocean exists in zones where sunlight never reaches at all. This darkness is not night, it is constant, unbroken, and timeless. In these depths, there is no dawn or dusk, no seasons marked by changing light. The passage of time feels different here, measured instead by currents, pressure, and the slow drift of sinking particles from above. It is a world shaped by absence rather than illumination. Yet darkness does not mean emptiness. Life persists in remarkable forms. Creatures navigate using touch, vibration, chemistry, and sound. Some produce their own light. Others remain nearly invisible, blending perfectly into the black water. For humans, darkness often feels unsettling, but in the deep ocean it is simply normal. Evolution has shaped life to function without sight, replacing eyes with senses better suited to eternal night. As we descend, the ocean becomes quieter and slower, but never still. This dark realm covers more space than all forests, deserts, and grasslands combined, which leads naturally to the next idea. Because when most of the ocean is dark, it also means most of Earth's living space lies hidden far below the surface. When we think of habitats, we often imagine forests, ocean surfaces, or coral reefs. But the largest habitat on Earth lies far below, in the deep sea. Everything beneath roughly 200 meters of depth makes up the planet's greatest living space. This habitat stretches across more than half of Earth's surface and plunges miles downward. It surrounds continents, fills basins and blankets underwater mountains and plains. By volume, it dwarfs all other ecosystems combined. Life here moves slowly. Food is scarce. Temperatures are cold. Pressure is immense. Yet countless species survive, adapted to conditions that seem impossible from the surface. Many have never been seen by human eyes. Because the deep sea is so vast, even small discoveries matter. A single expedition can reveal dozens of new species. Each one adds to our understanding of how life adapts and endures. This habitat also plays a crucial role in global systems. It stores carbon, circulates nutrients, and connects surface ecosystems through slow, unseen processes. As we continue drifting downward, the scale of this hidden world becomes harder to grasp, and with greater depth comes greater force. Because in the deep sea, pressure increases steadily, shaping everything that lives there. As we sink deeper into the ocean, pressure builds quietly and relentlessly. For every 10 meters of depth, the pressure increases by 1 atmosphere, the same force we feel from the entire weight of air above us at sea level. By the time you reach 1,000 meters, the pressure is 100 times greater than at the surface. At the deepest trenches, it exceeds 1,000 atmospheres. This force is strong enough to crush steel, collapse submarines, and destroy unprotected equipment instantly. Yet life persists. Deep-sea creatures are not fighting pressure. They are built for it. Their bodies contain little empty space. Bones are soft or absent. Cells are reinforced with special proteins that keep them functioning under extreme force. To these organisms, pressure is not an obstacle. It is simply the environment they were born into. They drift, feed and reproduce without noticing the crushing weight above them. For humans, pressure feels threatening because it is unfamiliar. But in the deep ocean, it is constant and stable, changing only with depth. As pressure continues to increase, the seafloor draws closer, and eventually, all this force gathers at a single place, the deepest point in the ocean, a place called Challenger Deep. At the very bottom of the ocean lies Challenger Deep, the deepest known point on Earth. It is located within the Mariana Trench in the Western Pacific Ocean, more than 10,000 meters below the surface. This depth is difficult to imagine. If you placed Mount Everest into Challenger Deep, its peak would still be buried under more than a mile of water. The pressure here is over 1,000 times greater than at sea level. Only a handful of crude submersibles have ever reached this place. Each descent takes hours, passing slowly through layers of water into total darkness. When they arrive, they find a silent, alien landscape shaped by immense force. The seafloor at Challenger Deep is cold, nearly freezing, and covered in fine sediment. Despite the extreme conditions, life exists here. Small crustaceans, microbes, and strange fish adapted to this crushing environment continue to survive. Challenger Deep reminds us that Earth still holds places as remote as any distant planet, and it challenges our assumptions about where life can exist. As we leave this deepest point behind, another comparison begins to take shape. Because Challenger Deep is not just deep, it is deeper than Earth's tallest mountain is tall. Mount Everest rises nearly 9,000 meters above sea level, standing as Earth's tallest peak. Challenger Deep descends even farther in the opposite direction. Its depth exceeds Everest's height by more than a mile. This comparison helps translate abstract numbers into something more tangible. Imagine standing on Everest's summit, then continuing downward through air, water, and darkness for thousands of additional meters. That is the scale of the ocean's depth. Mountains feel dramatic because we can see them. Trenches feel abstract because they are hidden. Yet in sheer size, the ocean's valleys surpass the planet's highest landforms. This vertical scale shapes life in profound ways. Organisms living at such depths experience conditions unlike anything on land. Temperature remains stable. Light is absent. Pressure dominates every aspect of existence. The idea that Earth's greatest heights are matched by even greater depths reminds us that our planet is balanced in extremes. What rises above the surface is mirrored by what sinks below it. As this symmetry settles in, another surprising truth emerges. Despite our technology and exploration, very few humans have ever traveled to the ocean's deepest places. Since humans first explored the planet, reaching the ocean's deepest points has remained an extraordinary challenge. Fewer people have descended to Challenger Deep than have walked on the surface of the Moon. The difficulty is not distance, but pressure. Building vessels strong enough to withstand the crushing force of the deep sea requires precise engineering and enormous resources. Each mission carries risk, expense, and uncertainty. Most deep-sea exploration is done by robotic vehicles, not humans. These machines send back images and data, revealing landscapes no one has ever seen directly. Even then, vast areas remain unmapped. This imbalance is striking. We have detailed maps of distant planets, yet much of our own ocean floor is still unknown. Entire ecosystems exist beyond our reach, unseen and undocumented. The rarity of human presence in the deep sea adds to its mystery. It remains a place largely untouched by civilization, operating on its own timescales and rules. As we reflect on this, another thought arises gently. Perhaps the reason the deep ocean feels so alien is because, in many ways, it truly is. Even compared to space, the deep sea presents unique challenges. At first, space seems like the ultimate frontier. Vacuum, radiation, and distance make it feel distant and hostile. Yet in many ways, the deep sea is even more extreme. Pressure replaces emptiness. Darkness replaces stars. Water presses from every direction. In space, astronauts float in near weightlessness. In the deep ocean, pressure increases relentlessly. A spacecraft can be built to withstand vacuum more easily than a vessel can resist crushing force. The deep sea also hides life that looks unfamiliar. Transparent bodies, glowing organs, and shapes unlike anything on land give the impression of another world. Many deep-sea creatures resemble ideas from science fiction more than familiar animals. Communication is harder underwater. Signals travel differently. Light disappears quickly. Even sound bends and carries in unexpected ways. Because of this, the deep ocean often feels less explored, less understood, and more mysterious than space. It is right beneath us, yet psychologically distant. As we drift further into this alien realm, the idea of survival becomes even more astonishing. Because in places where machines struggle, life continues calmly, thriving under pressures that would destroy submarines. In the deepest parts of the ocean, pressure would instantly destroy most human-made structures. Steel bends, glass shatters, electronics fail. Yet living organisms move through these environments without harm. Deep-sea creatures survive by being flexible rather than rigid. Their bodies contain little air, leaving nothing to compress. Their cells are reinforced with specialized molecules that stabilize proteins under extreme pressure. Some fish have soft bones or no bones at all. Others rely on gelatinous tissues that adapt naturally to their surroundings. Instead of resisting pressure, they exist in balance with it. This approach allows life to flourish where engineering struggles. It is a reminder that evolution often solves problems in ways humans would never consider. Simplicity and adaptation replace strength and resistance. Even microorganisms survive buried beneath layers of sediment, feeding on chemical energy instead of sunlight. Life persists quietly, steadily, without drama. As we consider this resilience, the deep ocean begins to feel less hostile and more alive. And yet, despite all this life, the darkness remains profound, which leads us to another quiet truth. In the deep sea, darkness is not emptiness. It is simply another condition life has learned to inhabit. In the absence of sunlight, the deep ocean might seem like a void. But darkness here is full of activity. Life drifts, hunts, feeds, and reproduces without ever seeing the sun. Particles of organic matter fall slowly from above, like underwater snow. These fragments feed entire food webs, sustaining creatures far below the surface. Every sinking particle carries energy into the dark. Some animals glow softly, lighting brief moments in the black water. Others remain invisible, relying on silence and stillness. Sound travels farther here than sight, becoming the ocean's primary language. Even the seafloor is alive. Microbes thrive within sediments. Strange fish hover just above the bottom. Crustaceans crawl slowly, conserving energy. Darkness does not mean absence. It means adaptation. Life fills the space in quiet, efficient ways without wasted motion. As this realization settles, the journey naturally continues. Because beyond darkness and depth, the ocean hides landscapes as dramatic as anything on land. Mountains, valleys, and ridges rise and fall beneath the waves, waiting to be discovered next. As we move beyond darkness, shape begins to matter. Beneath the ocean's surface, the seafloor is far from flat. It is sculpted into vast mountain ranges that stretch farther than any chain found on land. These underwater ranges wind across the planet, hidden beneath miles of water. The largest of these systems is so extensive that, if lifted above the surface, it would dwarf the Himalayas in length. Peaks rise, valleys fall, and ridges snake across entire ocean basins, forming a continuous network of stone. These mountains are not ancient remnants worn down by time. Many are geologically young, constantly reshaped by forces beneath Earth's crust. Magma rises, cools, and forms new rock, slowly building the seafloor outward. Because they lie hidden, these ranges rarely enter human imagination, yet they influence ocean currents, guide marine life, and shape the chemistry of the sea. They are foundations upon which ecosystems form. To picture these mountains is to realize how much of Earth's grandeur exists unseen. Vast landscapes lie beneath calm surfaces, unnoticed by those above. And among all these submerged ranges, one stands out for its sheer scale, a ridge that stretches like a scar across the Atlantic, quietly reshaping the planet below. Running down the center of the Atlantic Ocean is the Mid-Atlantic Ridge, the longest mountain chain on Earth. It stretches for more than 40,000 miles, winding from the Arctic Ocean all the way to the Southern Ocean, hidden beneath deep water. This ridge marks a boundary where tectonic plates slowly pull apart. As they separate, molten rock rises from below, cools, and forms new ocean floor. Inch by inch, year by year, the Atlantic grows wider. Unlike mountains on land, the Mid-Atlantic Ridge is not shaped by erosion or weather. It is shaped by creation. New rock is born here constantly, adding fresh surface to the planet. In a few places, the ridge rises high enough to break the surface. Iceland is one such place, where volcanic activity and glaciers coexist above the waves, offering a rare glimpse of this hidden system. Though invisible to most people, the Mid-Atlantic Ridge plays a crucial role in Earth's geology. It drives seafloor spreading and connects oceans into a single dynamic system. As this slow creation continues beneath us, it naturally leads to another idea. The ocean floor is not static. It is alive with fire, reshaped by volcanoes hidden below the waves. When we imagine volcanoes, we picture fiery mountains on land. But most volcanic activity on Earth happens underwater. Beneath the ocean, thousands of volcanoes quietly reshape the planet's surface. Along mid-ocean ridges and hotspots, magma rises from deep within Earth, pushing through cracks in the crust. When it meets cold seawater, it cools rapidly, forming new rock in strange, rounded shapes. This process builds the seafloor piece by piece. Many underwater volcanoes erupt without ever being noticed. Their lava cools in darkness, unseen by human eyes. Others erupt with enough force to send plumes of ash and gas upward through the water, altering local ecosystems. Over time, repeated eruptions can build massive seamounts. Some grow tall enough to break the surface, forming islands. Others remain hidden, their peaks just below the waves. These volcanoes are not just geological features. They release minerals into the water, feeding chemical reactions that support unique life forms. As magma continues to rise and cool beneath the sea, another truth becomes clear. Earth's volcanic heart beats strongest not on land, but beneath the ocean itself. The majority of Earth's volcanic eruptions occur beneath the ocean, far from human observation. Stretching along mid-ocean ridges, volcanic zones encircle the planet like glowing seams hidden underwater. These eruptions are rarely explosive. Instead, lava flows steadily, cooling almost instantly as it meets the surrounding sea. This gentle but constant activity produces new crust, renewing the ocean floor over millions of years. Because seawater absorbs heat quickly, underwater eruptions often go unnoticed. There are no towering ash clouds, no roaring flames visible from afar. Yet the total volume of lava produced beneath the ocean exceeds that on land. This hidden volcanism drives seafloor spreading, shapes underwater landscapes and releases minerals that nourish deep-sea ecosystems. Without it, the ocean floor would be ancient and stagnant. The contrast is striking. On land, volcanoes feel dramatic and dangerous. Underwater, they are patient and persistent, working quietly over immense spans of time. As this unseen activity continues, it sometimes reaches a tipping point. Occasionally, the slow building of volcanic rock rises high enough to meet air instead of water, and when that happens, the ocean gives birth to entirely new land. Sometimes underwater volcanoes grow tall enough to break through the ocean's surface. When this happens, a new island is born. Steam rises, rock hardens, and land appears where there was once only water. These newborn islands often begin as violent events. Lava meets seawater, producing clouds of ash and gas. Over time, repeated eruptions pile rock upon rock, allowing the island to grow and stabilize. Some islands survive only briefly. Waves erode their fragile slopes, pulling them back beneath the sea within years. Others endure, becoming permanent features of the planet. The Hawaiian Islands were formed this way, rising slowly over millions of years as volcanic hotspots fed continuous eruptions. Iceland, too, owes its existence to submarine volcanic activity along the mid-Atlantic ridge. To witness an island's birth is to see Earth reshaping itself in real time. It reminds us that the map of the world is not fixed, but alive. Yet, creation is only half the story. Just as the ocean can give rise to land, it can also reclaim it, which leads naturally to the next thought. Some islands once formed do not last forever. Not all islands are permanent. Many that rise from the ocean eventually sink back beneath the waves. Erosion, shifting tectonic plates, and rising sea levels slowly wear them down or pull them under. Volcanic islands are especially vulnerable. Once eruptions stop, the weight of the island can cause the crust beneath it to sink. Waves grind away at its edges, carrying rock back into the sea. Over time, coral reefs may grow around the sinking island, forming rings known as atolls. Eventually, the original land disappears entirely, leaving only coral encircling a shallow lagoon. This cycle of birth and disappearance happens over thousands to millions of years. It is slow enough to feel permanent within a human lifetime, yet inevitable on geological scales. Entire island chains have followed this pattern, rising, eroding, and vanishing. The ocean quietly records these changes in layers of sediment and coral. As we reflect on these cycles, the ocean feels less like a static place and more like a sculptor, constantly shaping, reshaping, and redistributing the planet's surface. And beneath all this change lies another vast feature: broad, flat regions that stretch for thousands of miles, forming the deepest plains on Earth. Beyond mountains and trenches, much of the ocean floor is made up of immense flat regions called abyssal plains. These plains stretch across thousands of miles, forming some of the largest continuous landscapes on Earth. They are shaped by time and gravity. Sediment slowly rains down from above, settling into low areas and smoothing rough terrain. Over millions of years, this process creates wide, level expanses in the deepest parts of the ocean. The abyssal plains are cold, dark, and quiet. Water temperatures remain near freezing. Food arrives slowly, drifting down from surface waters. Life here moves at a patient pace. Despite their emptiness, these plains play a vital role in Earth systems. They store carbon, recycle nutrients, and support specialized organisms adapted to scarcity. From a human perspective, they feel distant and abstract. But they cover more area than all continents combined, making them one of Earth's dominant environments. As we drift across these silent plains, another dramatic feature comes into view, because even these flat regions are interrupted by sudden drops, immense valleys carved beneath the sea rivaling the greatest canyons on land. Hidden beneath the ocean are vast canyons cut deep into the sea floor. These submarine canyons can be as steep and dramatic as the Grand Canyon, sometimes even deeper. They form through a combination of processes. Ancient rivers once carved valleys when sea levels were lower. Later, underwater landslides and powerful currents deepened these cuts, carrying sediment down toward the abyss. Monterey Canyon, off the coast of California, plunges deeper than the Grand Canyon and stretches far out to sea. Yet it remains invisible from the surface, its scale hidden beneath calm water. These canyons act like highways for nutrients. Sediment flows through them, feeding deep-sea ecosystems that rely on organic matter from above. Marine life often gathers along canyon walls, where currents bring food and shelter. Whales, fish, and invertebrates depend on these hidden valleys. Submarine canyons remind us that Earth's most dramatic landscapes are not limited to dry land. Some of the deepest scars lie underwater, carved patiently by forces we rarely see. And sometimes, those forces move suddenly. When sediments shift all at once, the ocean floor can change in moments, leading us to the next quiet truth. Just like on land, landslides occur beneath the ocean. Vast amounts of sediment can suddenly give way, tumbling down slopes and into deeper basins. These underwater landslides can move more material than any landslide on land. They are often triggered by earthquakes, volcanic activity, or the slow buildup of unstable sediment. When they occur, they reshape the seafloor in minutes, carving new channels and burying existing ecosystems. Some underwater landslides are powerful enough to generate tsunamis. The sudden displacement of water sends waves racing across the ocean, sometimes reaching distant shores. Despite their power, most submarine landslides go unnoticed by humans. They happen far below the surface, in darkness and silence. Over geological time, these events play a major role in shaping underwater landscapes. They redistribute sediment, alter habitats, and influence ocean chemistry. As we consider this hidden motion, it becomes clear that the seafloor is not a stable foundation. It is dynamic and alive with movement. And beneath all this shifting terrain lies an even deeper process, one that moves continents themselves. The slow, steady motion of Earth's tectonic plates beneath the sea. Beneath the ocean floor, enormous tectonic plates slide slowly over Earth's mantle. These plates carry continents, shape oceans, and drive the planet's long-term change. Most of their boundaries lie underwater. Where plates pull apart, new seafloor forms. Where they collide, one plate may sink beneath another, creating deep trenches and powerful earthquakes. These processes happen constantly, though far too slowly to feel. The ocean hides most of this activity. Trenches, ridges, and faults lie beneath miles of water, shaping the planet in silence. Over millions of years, oceans open and close as plates rearrange the surface of the Earth. This motion explains why continents once fit together and why fossils of the same species appear on distant shores. It also explains why the ocean floor is younger than most land, continually recycled by tectonic forces. The ocean is not just water resting on rock. It is the visible surface of a living, moving planet. As this realization settles, our journey naturally shifts from stone and motion back to water itself, because beyond landscapes and plates, the ocean is defined by movement. waves, tides, and energy traveling endlessly across its surface, waiting to be explored next. As the solid world beneath the sea continues to shift, the ocean's surface tells a different story. Waves appear and disappear along coastlines, but many begin far beyond the horizon. Some waves travel thousands of miles across open ocean before ever reaching land. These long-distance travelers are called swells. Born from powerful storms, they carry energy, not water, across vast distances. Each wave passes through the sea, transferring motion forward while the water itself mostly stays in place. A storm in the Southern Ocean can send waves rolling toward distant beaches weeks later. By the time they arrive, the wind that created them may be long gone, yet its influence remains, translated into steady, rhythmic motion. Surfers often ride waves that began as storms on the other side of the planet. To them, each swell is a message from far away, delivered silently across the sea. This ability to carry energy over immense distances reveals the ocean's connected nature. What happens in one place rarely stays there. As waves continue their quiet journeys, another realization emerges. The ocean remembers storms long after the skies have cleared, and sometimes that stored energy gathers into something rare and sudden, rising without warning from an otherwise calm sea. Long after a storm fades from the sky, its presence can still be felt at sea. Swells carry the memory of wind and pressure systems that no longer exist, preserving their energy as gentle, repeating waves. Unlike choppy local waves, swells are smooth and evenly spaced. They move with calm persistence, shaped by distance and time. The farther they travel, the more refined their rhythm becomes. This transformation happens as chaotic motion settles into order. The ocean filters out irregular energy, leaving behind long rolling waves that feel almost deliberate. Each crest is a quiet echo of turbulence far away. For coastal ecosystems, swells matter deeply. They influence erosion, move sediment, and shape shorelines over centuries. Coral reefs and beaches are sculpted by these distant forces, arriving patiently, wave after wave. To stand at the shore and watch swells arrive is to witness a delayed conversation between atmosphere and ocean. The sky once spoke with wind and storm. The sea now replies in motion. As this slow exchange continues, it sometimes intensifies. Under certain conditions, waves can combine their energy into something far more dramatic. A single wall of water rising unexpectedly from the surrounding sea. This leads us gently to the next phenomenon: rogue waves. The tallest ocean waves rarely appear near land. They form far from shore, in open water where wind, distance, and time align. Here, storms have room to build energy uninterrupted. Recorded waves in the open ocean have exceeded 30 meters in height, taller than 10-story buildings. These giants rise when strong winds blow consistently over long distances, allowing energy to stack into immense moving walls. Unlike waves that break on beaches, these waves travel with steep faces and tremendous force. Ships encountering them describe moments when the sea seems to stand upright. These waves are not permanent features. They rise, move forward, and eventually disperse, releasing energy back into the ocean. Yet during their brief existence, they carry power capable of reshaping vessels and altering the surface. To the ocean, such waves are expressions of balance and imbalance. Energy builds, releases, and returns to motion. As dramatic as these waves are, they are still part of surface dynamics. Another kind of wave exists that behaves very differently, one driven not by wind, but by sudden displacement of water itself, a wave that can cross entire oceans. a tsunami. Tsunamis are among the most powerful waves on Earth. Unlike surface waves driven by wind, tsunamis are created when massive volumes of water are suddenly displaced, often by earthquakes, landslides, or volcanic eruptions beneath the sea. In deep water, a tsunami may pass unnoticed. Its wave height can be small, sometimes less than a meter, while its energy spreads across the entire depth of the ocean. But as it approaches shallow water, that energy compresses and the wave rises dramatically. Tsunamis can travel at speeds exceeding 500 miles per hour, crossing entire ocean basins in a matter of hours. A wave born in one hemisphere can reach distant continents before a day has passed. The ocean becomes a messenger, carrying the force of geological events across the planet. Shores thousands of miles away feel the consequences of movements deep below the sea. Because of their speed and reach, tsunamis are monitored carefully. Sensors and warning systems track subtle changes in sea level to provide advance notice. As we reflect on these immense travelling waves, another quiet truth emerges. Many of the forces that create them begin far below the surface, where the ocean floor itself moves and breaks. Earthquakes that start in silence beneath the sea. A large number of Earth's earthquakes originate beneath the ocean floor. Tectonic plates meet, slide and lock together under miles of water, storing energy over years or centuries. When that energy releases, the seafloor shifts suddenly. These underwater earthquakes may go unnoticed at the surface, or they may send shock waves through the ocean, displacing water and triggering tsunamis. The same movement that feels distant beneath the sea can have far-reaching effects above it. Because most plate boundaries lie underwater, the ocean hides much of Earth's seismic activity. Trenches and fault lines trace invisible paths across the sea floor, marking zones of tension and release. Seismographs around the world listen constantly for these movements. Even the smallest tremors leave signatures that travel through Earth's crust. The ocean acts as both cover and conduit. It conceals the origin of earthquakes while transmitting their energy outward. As these forces ripple through water and rock, the ocean reminds us that stillness is often deceptive. Beneath calm surfaces, powerful motion is always present. This hidden activity also shapes the shoreline itself, because when seismic forces move water toward land, the boundary between sea and shore can change suddenly, leading us into the next realization. Storm surges and seismic waves reshape coastlines. When powerful storms move across the ocean, they do more than stir waves. Strong winds and low atmospheric pressure push large volumes of water toward the shore, creating storm surges. These surges can raise sea levels several meters above normal. Unlike regular tides, storm surges arrive suddenly. They flood coastlines, cover roads, and reshape beaches in a matter of hours. During major hurricanes, storm surges can rise higher than buildings, carrying debris far inland. The ocean's surface responds directly to the atmosphere above it. Wind presses against water, transferring energy downward and forward. As water piles up, gravity eventually forces it onto land. Storm surges are often the most destructive part of coastal storms. Even when wind damage is limited, rising water can overwhelm communities and ecosystems. Over time, repeated surges reshape coastlines. Sand moves, inlets form, barrier islands shift position. These changes remind us that coastlines are temporary boundaries, not fixed edges. The ocean and land are always negotiating space. As we observe this constant exchange, another gentle rhythm becomes apparent. Not all ocean movement is sudden or violent. Some motion follows a predictable pattern, guided by celestial forces above us, the steady rise and fall of tides. Twice each day, the ocean rises and falls along coastlines around the world. This motion, known as tides, is driven primarily by the Moon's gravitational pull. As the Moon orbits Earth, it draws ocean water toward it, creating bulges on opposite sides of the planet. As Earth rotates, coastlines move through these bulges, experiencing high and low tides in a regular rhythm. The Sun also influences tides, sometimes strengthening them and sometimes softening them, depending on alignment. Tides shape coastal ecosystems. Many marine creatures time their feeding, reproduction, and movement to the rise and fall of the water. Tidal pools fill and empty. Mudflats appear and disappear. For humans, tides have guided navigation for thousands of years. Sailors learn to read the water, waiting for favorable tides to enter harbors or cross shallow passages. Unlike storms or waves, tides are predictable. They follow celestial mechanics, linking the ocean to the Moon in a quiet gravitational dance. As this steady rhythm continues, it occasionally reaches extremes. Certain alignments cause tides to rise higher than usual, revealing the ocean's reach in dramatic ways. These are known as king tides. King tides are the highest tides of the year. They occur when the Moon, Sun, and Earth align in a way that amplifies gravitational pull, drawing ocean water farther onto land than usual. During king tides, coastal roads may flood, beaches disappear, and seawater reaches places normally dry. These events are temporary, lasting only a few hours, but they offer a glimpse of what higher sea levels could look like in the future. Scientists and coastal planners study king tides carefully. They provide real-world examples of how rising seas may affect communities as the climate warms. What happens briefly during a king tide may become more common over time. Photographers often document these events, capturing images of waves lapping at streets and sea walls. The ocean appears calm, yet it quietly claims space beyond its usual boundary. King tides remind us that the ocean's edge is not fixed. It shifts with gravity, temperature, and time. As water recedes again, the coastline returns to familiar shape. But the memory of that reach remains. This rhythmic expansion and retreat leads us gently to another truth. Even when the sea appears calm, it is part of a larger cycle of motion, energy, and balance. The ocean is never truly still. When the ocean's surface appears calm, motion has not stopped. It has simply become subtle. Beneath smooth reflections, currents continue to flow, tides rise and fall, and energy moves invisibly through water. Calm seas often indicate balance rather than absence. Winds may be light, waves small, but the ocean's deeper systems remain active. Heat transfers slowly, salinity gradients shift, life drifts and feeds. This quiet movement is essential. It maintains oxygen levels, distributes nutrients, and supports ecosystems far below the surface. Without it, the ocean would stagnate. The illusion of stillness comes from scale. Human senses are tuned to quick changes. The ocean operates on longer timescales, where motion unfolds over hours, days, and centuries. To float on calm water is to rest atop immense activity, like lying on the surface of a breathing world. As this realization settles, the journey naturally begins to descend again, because beneath motion and surface energy lies a different kind of life, one that thrives without sunlight, powered by chemistry and heat. The deep ocean's hidden ecosystems await next. As we descend further, sunlight disappears completely, yet life continues. In the deepest parts of the ocean, entire ecosystems exist without relying on the sun. Instead of photosynthesis, these communities are powered by chemistry. At hydrothermal vents, seawater seeps into cracks in the seafloor, heats near molten rock, and erupts back into the ocean rich with minerals. Bacteria use these chemicals as an energy source through a process called chemosynthesis. This energy becomes the foundation of a complete food web. Worms, crabs, shrimp, and clams gather around these vents, feeding directly on bacteria or on animals that consume them. Life flourishes in total darkness, surrounded by water hot enough to melt lead. This discovery transformed biology. It proved that sunlight is not the only way to sustain life. Energy, in many forms, can support living systems. These ecosystems also reshaped ideas about life beyond Earth. If organisms can thrive here, they might exist beneath icy moons or distant oceans elsewhere. As this idea settles, the ocean begins to feel less limited by surface rules. And that realization leads gently deeper, because in some places, life survives not just without light, but near extreme heat itself. Hydrothermal vents were discovered in the late 20th century, revealing one of the ocean's most astonishing environments. Rising from the seafloor like chimneys, these vents release superheated water filled with dissolved metals and minerals. The water can reach temperatures exceeding 700 degrees Fahrenheit, yet life thrives nearby. Specialized bacteria convert chemicals in the vent fluid into energy, forming the base of a dense and active ecosystem. Giant tube worms grow taller than humans, anchored to the vents. They lack mouths and stomachs, relying entirely on bacteria living inside their bodies for nourishment. Crabs and shrimp swarm the vents, feeding and reproducing in the perpetual darkness. These communities exist in sharp contrast to their surroundings. Beyond the vent fields, the seafloor is sparse and quiet. Near the vents, it is crowded and alive. Hydrothermal vents show how uneven life in the ocean can be. Energy creates islands of abundance in otherwise empty places. As we linger here, another surprising fact emerges. Some organisms near these vents survive temperatures that seem completely impossible for life. Conditions that would destroy most known forms, yet here they persist calmly. Near hydrothermal vents, temperatures rise to extremes that challenge our understanding of biology. Water emerging from these vents can be hot enough to melt metal, yet certain organisms survive just centimeters away. These organisms are known as extremophiles. Their cells contain proteins specially structured to remain stable under intense heat. Instead of breaking apart, their biological machinery functions normally where others would fail. Some bacteria thrive at temperatures above 200 degrees Fahrenheit. They use chemical reactions to fuel their metabolism, independent of sunlight and conventional food sources. Their existence stretches the definition of where life can survive. The surrounding water cools rapidly, creating steep temperature gradients. Life clusters precisely where conditions are tolerable, forming narrow bands of activity along the vent structures. These environments feel hostile, yet they are stable. Heat flows continuously, providing a steady energy source. Over time, evolution has refined survival here. As we consider these heat-loving organisms, another extreme comes into view. Because the deep ocean is not only hot in places, it is also cold beyond imagination, near freezing, under crushing pressure, where different forms of life endure quietly. Away from hydrothermal vents, the deep ocean is intensely cold. Temperatures hover just above freezing, remaining stable year-round. In these conditions, life slows but does not stop. Fish, invertebrates, and microbes have adapted to function at temperatures that would quickly disable warm water species. Some produce antifreeze proteins in their blood, preventing ice crystals from forming within their cells. Movement here is deliberate and efficient. Energy is conserved. Growth is slow. Some deep-sea animals may live for decades or longer, aging at a pace far slower than surface species. The cold also preserves. Organic matter breaks down slowly, allowing remains to persist on the seafloor for long periods. This creates a quiet archive of biological material. Despite the cold, reproduction continues. Life cycles unfold patiently, guided by stability rather than speed. As we drift through this chilled darkness, the contrast becomes clear. The deep ocean holds extremes side by side, heat and cold, pressure and stillness, and yet temperature is only one challenge. Another force presses constantly in the deep, one that shapes every movement and structure. The immense pressure that defines life below the surface. In the deep ocean, pressure is the defining condition. With every meter of descent, the weight of water above increases, pressing inward from all directions. Life here is built around this constant force. Deep-sea organisms avoid rigid structures. Instead, they are flexible, compressible, and resilient. Many lack air-filled spaces entirely, leaving nothing for pressure to collapse. Cell membranes are reinforced. Enzymes are adapted to function under force. Even genetic processes adjust to the environment, ensuring stability where pressure would otherwise disrupt life. Fish living at depth often have soft bones and delicate tissues. Jelly-like bodies are common, allowing organisms to drift effortlessly rather than resist movement. Pressure also influences behavior. Rapid movement is rare. Sudden changes are avoided. Everything unfolds slowly and efficiently. To humans, pressure feels threatening, but in the deep sea, it is simply normal. Life is not struggling against it. It exists because of it. As this realization settles, the deep ocean begins to feel less hostile and more finely tuned. A place where conditions are extreme, yet perfectly balanced. And within that balance, some creatures have developed an ability that feels almost magical. They create light in the darkness. In a world without sunlight, many deep-sea creatures produce their own light. This phenomenon, known as bioluminescence, is created through chemical reactions within their bodies. Tiny plankton can make the ocean glow when disturbed, turning waves into fields of shimmering blue light. Larger creatures use glowing organs to attract prey, communicate, or camouflage themselves against faint light from above. Bioluminescence serves many purposes. Some animals flash suddenly to startle predators. Others glow softly to blend into the surrounding darkness. Anglerfish dangle luminous lures to draw curious prey close. The chemistry behind this light is efficient. Nearly all energy becomes illumination, producing little heat. In the cold, deep sea, this efficiency is essential. Entire ecosystems communicate through light rather than sound or sight. Flashes, pulses, and glows replace visual signals from the surface world. To imagine the deep ocean is to imagine a drifting galaxy, points of light appearing and fading in endless darkness. As these glowing signals move through the water, another pattern emerges. Some of the ocean's largest migrations happen invisibly each night, guided not by light, but by instinct and rhythm. Every night, as darkness spreads across the ocean's surface, a vast migration begins below. Billions of small organisms rise from the depths towards shallower waters. This movement is known as diel vertical migration. Plankton, tiny shrimp-like creatures, and small fish ascend to feed on microscopic plants near the surface. Larger predators follow, creating a moving column of life that stretches for hundreds of meters. At dawn, the entire mass retreats back into the deep, avoiding surface predators and sunlight. This migration happens every day across oceans worldwide. It is the largest daily movement of life on Earth. Despite its scale, it is rarely seen. The ocean surface remains calm while this hidden tide flows beneath. This migration plays a crucial role in the planet's systems. It moves carbon from the surface into the deep ocean, helping regulate Earth's climate. As we picture this silent rhythm, the ocean feels alive with routine and order. And it leads naturally to another quiet mystery. In some deep places, water itself behaves strangely, forming lakes and rivers beneath the sea. Deep beneath the ocean's surface, there are places where water forms pools and streams, much like lakes and rivers on land. These features are created by brine, extremely salty water that is denser than surrounding seawater. When brine seeps from the sea floor, it settles into depressions, forming shimmering pools with clear boundaries. These brine lakes have shorelines, waves, and currents, all contained within the ocean. To submersibles, they appear surreal. A body of water resting inside another body of water, separated by density rather than land. The surface of these lakes ripples like liquid glass. Most marine life cannot survive within brine pools. The salt concentration is deadly. But at the edges, specialized organisms thrive, adapted to this sharp chemical boundary. These environments feel alien, challenging assumptions about how water behaves. They remind us that even familiar substances act differently under extreme conditions. As we drift away from these hidden lakes, another subtle force reveals itself. The ocean is not only shaped by water and rock, but by time itself. Slow, patient, and nearly imperceptible change. Far below the waves, the ocean floor is slowly splitting open. Along mid-ocean ridges, tectonic plates pull apart, allowing molten rock to rise from Earth's mantle. As this magma cools, it forms new crust. This process, known as seafloor spreading, happens continuously. The movement is slow, measured in centimeters per year, but over millions of years it reshapes the planet. Entire oceans are born this way. The Atlantic Ocean began as a narrow rift between continents that gradually widened. Even today, it continues to expand, quietly growing broader with time. As new crust forms, older seafloor is pushed outward, eventually sinking back into the mantle at deep trenches. The ocean floor is recycled, younger than most land. This slow spreading connects oceans into a dynamic system. Nothing beneath the sea is truly permanent. As we consider this patient motion, the ocean begins to feel like a breathing planet, expanding, contracting, renewing itself endlessly. And this movement affects more than geology. It influences earthquakes, tsunamis, and the shape of continents. Which brings us gently to another force born in the ocean's depths, the origin of many earthquakes and seismic waves. Tsunamis often begin far below the ocean's surface, where tectonic plates suddenly shift. When one plate slips beneath another, the seafloor can rise or fall in seconds, displacing enormous volumes of water. This sudden movement sends energy upward through the ocean. In deep water, the resulting wave may be nearly invisible, spreading outward at high speed. As it reaches shallow areas, the energy compresses and the wave grows dramatically. Unlike wind-driven waves, tsunamis move the entire column of water from surface to seafloor. Their power comes from depth as much as speed. The ocean becomes a transmitter, carrying geological motion across entire basins. Shores far from the earthquake feel the result of distant shifts beneath the sea. Warning systems now listen for these changes, using sensors and satellites to track subtle sea level variations. Even so, tsunamis remain humbling reminders of Earth's power. As this force fades back into stillness, the ocean resumes its quiet rhythms, and from these depths, our journey will soon rise again toward creatures, history, and the ancient survivors shaped by this restless, living sea. As the deep ocean settles back into stillness after seismic motion, darkness returns. Yet it is not an empty darkness. Across the water, countless organisms generate light from within their own bodies. This ability, called bioluminescence, is one of the ocean's most widespread adaptations. From tiny plankton to large squid, light appears as soft glows, quick flashes, or steady beams. The light is created through chemical reactions involving special molecules and enzymes, releasing energy almost entirely as illumination. For some creatures, light is a warning. A sudden flash can confuse or startle predators. For others, it is a disguise, matching faint light from above to erase their silhouette. Some species use light to communicate, signaling mates or rivals in the dark. In the vast deep, where vision is limited, light becomes language. Patterns replace colours, timing replaces shapes. To imagine the deep sea is to imagine a slow constellation, points of blue and green drifting silently, appearing and fading without sound. As these living lights flicker across the water, they reveal a deeper truth. Darkness in the ocean is not absence, it is a canvas, and upon that canvas, life writes its presence softly, one glowing pulse at a time. Near the surface, bioluminescence takes on a different form. Microscopic plankton can light up entire stretches of ocean when disturbed. A breaking wave, a passing boat, even a swimmer's hand can trigger a radiant blue glow. This light is a defense mechanism. When plankton flash, they draw attention to predators, increasing the predator's risk of being seen by something larger. In this way, the smallest organisms influence the behavior of much larger ones. On calm nights, coastlines sometimes shimmer as waves roll in, glowing briefly before fading back into darkness. From above, the water looks alive with stars, mirroring the sky overhead. These glowing events remind us that even the most delicate forms of life can create breathtaking displays. The light lasts only seconds, but its effect lingers. Plankton also play a larger role. They form the base of marine food webs and help regulate Earth's climate by absorbing carbon dioxide. As the glow fades and the surface calms, the ocean returns to its quiet state. But beneath that calm, larger creatures move. Some carry lights not for defense, but for hunting in the endless dark below. In the deep ocean, where food is scarce and encounters are rare, the anglerfish has evolved a remarkable strategy. From its head extends a thin stalk tipped with a glowing lure. This light is produced by bioluminescent bacteria living within a special organ. The anglerfish drifts motionless, conserving energy. Its lure pulses softly in the darkness, mimicking the movement of prey. Curious fish swim closer, drawn by the glow, unaware of the danger. In a sudden motion, the anglerfish opens its mouth, engulfing the unsuspecting victim. The hunt is over almost instantly. This strategy reflects the deep sea's economy. Movement is costly. Energy must be conserved. The anglerfish waits rather than searches. Female anglerfish grow much larger than males. In some species, tiny males fuse permanently to the female's body, becoming part of her reproductive system. It is an unusual solution to finding mates in a vast, empty world. As the anglerfish drifts back into stillness, its lantern continues to glow, a single point of light suspended in black water, and nearby other creatures move differently. Some do not hunt alone, but as part of vast, unseen journeys happening every night. Each night, as darkness spreads across the ocean's surface, a massive migration begins below. Trillions of small organisms rise from the deep toward shallower waters. This movement is known as diel vertical migration. Plankton ascend to feed on microscopic plants near the surface. Fish follow the plankton. Squid and larger predators follow the fish. The entire food web moves upward together. At dawn, the process reverses. The creatures sink back into the depths, escaping sunlight and surface predators. This migration happens daily across every ocean on Earth. Despite its scale, it remains invisible to most people. From above, the sea appears calm and unchanged. Below, life flows upward and downward like a breathing lung. This movement plays a vital role in Earth's climate. As organisms feed near the surface and return to depth, they transport carbon downward, helping regulate atmospheric levels. The ocean is not static. It pulses with routine, guided by light and darkness. As this great migration settles back into the deep, another hidden motion continues quietly below. Water itself moves slowly through the ocean, carrying heat and memory across the planet. Beneath the surface, vast currents move water across entire oceans. These currents form a global circulation system, often called the ocean conveyor belt. Driven by differences in temperature and salinity, it connects every major sea. Warm water travels from the equator toward the poles. Cold, dense water sinks and flows back toward lower latitudes. This movement can take hundreds or even thousands of years to complete a full cycle. These currents regulate Earth's climate. They distribute heat, keeping some regions warmer and others cooler than they would otherwise be. Without them, weather patterns would shift dramatically. The Gulf Stream, for example, carries warm water across the Atlantic, moderating Europe's climate. Other currents influence rainfall, storm paths, and marine ecosystems. Though powerful, these currents are slow and steady. Their influence is subtle but immense. Every wave breaking on a shore is connected indirectly to this hidden circulation. The ocean moves as one system, linking distant places through water and time. As we follow these currents in imagination, we begin to sense how connected the planet truly is, and this connection extends even further into sound itself, because the ocean is never silent. In the ocean, sound is the primary sense. Water carries sound waves faster and farther than air, allowing noises to travel across vast distances. For many marine animals, sound replaces sight. Whales communicate using low-frequency calls that can travel hundreds or even thousands of miles. These sounds move through deep water channels, echoing across entire ocean basins. Dolphins use clicks and whistles to navigate and hunt, creating detailed mental maps of their surroundings through echolocation. Even small fish produce sounds, grunting, drumming, or snapping to communicate. Coral reefs crackle with noise, shrimp snap their claws, fish call to one another. The reef becomes a living soundscape. Humans once thought the ocean was silent. Only with underwater microphones did we learn how full of sound it truly is. These soundscapes guide migrations, mating, and survival. They are as important as forests are to birds on land. As the echoes fade into distance, the ocean feels alive with conversation. And within these conversations, some creatures sing not just to communicate, but to create patterns passed down through generations. Among the ocean's many sounds, whale songs stand apart. Humpback whales produce long, complex sequences of notes that can last for hours. These songs are structured, repeating patterns rather than random noise. What makes them extraordinary is their reach. Low-frequency whale songs can travel thousands of miles through the ocean. A whale singing in one part of the sea may be heard far beyond the horizon. Even more remarkable, these songs change slowly over time. Whales within a population tend to sing the same version, and new variations spread gradually, almost like cultural trends. Scientists believe songs may play a role in mating or social bonding, though their full purpose remains mysterious. What is clear is that whales remember and learn these patterns. To imagine a song carried across an entire ocean is to imagine the sea itself listening. Water becomes both instrument and audience. As these deep voices fade into the distance, they leave behind a sense of continuity, a reminder that intelligence, memory, and culture exist beneath the waves. And some of that intelligence takes forms surprisingly familiar. Dolphins are among the ocean's most intelligent inhabitants. One of the most fascinating discoveries about them is their use of individual signature whistles. Each dolphin develops a unique sound that functions much like a name. Other dolphins recognize and respond to these whistles. They can even imitate another dolphin's call to get its attention. This suggests a level of self-awareness and social complexity once thought unique to humans. Dolphins live in fluid social groups, forming and reforming bonds over time. Names help maintain these connections across distance and movement. Their communication includes clicks, whistles, and body language. Together, these signals create a rich social world beneath the surface. This ability to identify individuals reflects memory, learning, and social awareness. Dolphins do not simply react, they recognize. As we drift with this idea, the ocean feels more familiar. Intelligence here is different but not distant, and dolphins are not alone. Other creatures also show problem-solving skills and curiosity. Some, with 8 arms and no bones, demonstrate a kind of intelligence that feels both alien and oddly relatable. Octopuses are masters of adaptation and problem-solving. Despite having no backbone and a short lifespan, they demonstrate remarkable intelligence. In laboratories and aquariums, octopuses have been observed solving puzzles, opening jars, and escaping enclosures. Each arm contains its own network of neurons, allowing it to act independently while remaining coordinated. This gives octopuses a distributed form of intelligence, unlike that of any other animal. In the wild, some octopuses carry coconut shells across the seafloor. They assemble these shells into shelters, using them as portable protection. This behavior is considered one of the clearest examples of tool use outside of mammals. Octopuses also show curiosity. They explore objects, manipulate their environment, and remember solutions to challenges. Their ability to change color and texture allows them to vanish instantly, blending perfectly with rocks, sand, or coral. As we imagine an octopus drifting through the deep, thinking, adapting, remembering, the ocean feels less mechanical, it feels mindful. And within this mindful world, there are also giants, creatures so large they challenge our sense of scale entirely. Among all creatures known to have existed on Earth, none surpasses the blue whale in size. Even the largest dinosaurs were smaller. A blue whale can grow up to 100 feet long and weigh more than 200 tons. Its heart is the size of a small car. Its blood vessels are wide enough for a human to crawl through. Yet, despite this immense scale, the blue whale feeds on some of the smallest animals in the ocean. Using baleen plates, it filters tiny krill from the water, consuming millions in a single day. This gentle feeding supports its enormous body. When a blue whale surfaces to breathe, its exhalation erupts into the air as a towering mist. The sound carries for miles. Despite their size, blue whales move gracefully. Their motions are slow, deliberate, and calm. To encounter one is to feel small in the best possible way, not diminished, but connected to something vast and ancient. As the blue whale slips back beneath the surface, the ocean returns to quiet motion, and from this calm we will continue toward time, history, and the ancient survivors still swimming in the deep. Long before dinosaurs walked the land, before forests covered the continents, jellyfish drifted through ancient seas. Fossil evidence shows they have existed for more than 500 million years, making them among the oldest animals still alive today. Jellyfish have no bones, no brains, and no blood. Their bodies are made mostly of water, soft and translucent, shaped by gentle pulses that carry them wherever the currents flow. Despite their simplicity, they have survived every major mass extinction. Their design has proven remarkably effective. With few moving parts and low energy demands, jellyfish thrive in environments where other creatures struggle. They bloom in warm waters, cold seas, shallow coasts, and deep darkness. Some species glow softly with bioluminescence. Others deliver powerful stings. Many drift silently, neither hunting nor fleeing, simply existing within the ocean's slow rhythms. Watching a jellyfish move feels like watching time itself drift by, unhurried, ancient, calm. As we consider how long jellyfish have endured, the ocean begins to feel timeless. A place where survival is not always about strength or speed. And among these ancient survivors, one small jellyfish carries an ability that seems to defy time entirely. Among the ocean's many strange creatures, one stands out for its extraordinary ability. The immortal jellyfish, scientifically known as Turritopsis dohoney, can reverse its own life cycle. When injured, stressed, or nearing death, this jellyfish can transform its adult body back into its earliest juvenile form. Instead of dying, it starts life again, growing once more into adulthood under the right conditions. This process does not make the jellyfish invincible. Predators, disease, and environmental changes can still end its life. But biologically, it does not have to age toward death in the way most organisms do. Inside its cells, genetic programs allow tissues to reorganize completely. Adult cells revert to a younger state, something scientists once thought impossible in complex animals. This ability has fascinated researchers studying aging and regeneration. While humans cannot do this, the jellyfish offers clues about how flexible life can be. Drifting unnoticed in warm oceans, this tiny creature quietly rewrites one of nature's most familiar rules. As this idea settles in, time itself feels different beneath the waves. And the ocean reminds us again that age, like distance, can behave strangely here. Sharks are far older than most people realize. They first appeared more than 400 million years ago, long before trees grew on land. At that time, Earth's surface was largely barren, while sharks already ruled the seas. Over hundreds of millions of years, sharks have survived multiple mass extinctions, including the event that ended the age of dinosaurs. Their basic body plan proved so effective that it changed very little over time. Streamlined shapes, powerful senses, and efficient movement allowed sharks to thrive in nearly every ocean environment. From shallow reefs to the open sea and deep waters, they adapted without needing dramatic redesign. Their skeletons are made of cartilage rather than bone, making them lighter and more flexible. Their skin is covered in tiny tooth-like scales that reduce drag as they swim. Sharks are not relics frozen in the past. They continue to evolve, but at a pace that favors stability over rapid change. To watch a shark glide through the water is to watch deep history in motion. a living connection to a world long before forests, flowers, or human footsteps existed on land. In the cold, dark waters of the North Atlantic lives a shark unlike any other. The Greenland shark moves slowly, grows slowly, and lives longer than any known vertebrate on Earth. Scientists estimate that some Greenland sharks can live for more than 400 years. Individuals alive today may have been swimming when Shakespeare was writing or when the first telescopes were turned toward the sky. Their secret lies in their environment and biology. Cold water slows metabolism. Slow movement conserves energy. Growth occurs at a pace measured in millimeters per year. Greenland sharks reach lengths of over 20 feet, yet they drift quietly through the deep, feeding on fish, squid, and even carrion. Their flesh contains toxins, making them unappealing to most predators. Studying these sharks has changed how scientists think about aging. Longevity, it seems, can be shaped by patience and stillness. As this centuries-long lifespan sinks in, time feels stretched beneath the waves. The ocean becomes a place where moments are measured not in seconds, but in generations, and some creatures have learned to live within that scale. For centuries, sailors told stories of enormous tentacled creatures rising from the deep, wrapping ships in their arms. These tales were dismissed as legends, born from fear and imagination. Then evidence began to surface: massive scars on whales, enormous suckers washed ashore, and finally, photographs of the creature itself. The giant squid was real. Giant squid can grow longer than a bus, with eyes as large as basketballs. These eyes help them detect faint traces of light in the deep, allowing them to spot predators like sperm whales. They live far below the surface, rarely encountered by humans. Even today, sightings are rare, and much of their behaviour remains unknown. The confirmation of the giant squid reshaped our understanding of the ocean. It reminded us that disbelief does not equal impossibility. Somewhere in the dark, enormous creatures still drift unseen, moving through water deeper than light can reach. As this realization settles, the ocean feels wider, more mysterious, and the giant squid is not even the largest of its kind. Another relative, even more massive, waits deeper still. If the giant squid is impressive, the colossal squid is even more extraordinary. This deep-sea giant holds the record for the largest eyes of any animal ever known. Each eye can grow as large as a dinner plate, nearly a foot across. In the deep ocean, where light is scarce, such size allows the squid to detect even faint glimmers of bioluminescence. These eyes help the squid spot approaching predators, especially sperm whales, which are among the few animals capable of hunting them. In darkness, vision becomes a warning system rather than a tool for detail. Colossal squid are heavier and bulkier than giant squid, with rotating hooks on their tentacles instead of simple suckers. They are powerful, elusive, and rarely seen. Most of what we know comes from fragments found in whale stomachs or accidental captures. Live observations remain rare. To imagine such a creature drifting in the abyss is to imagine scale beyond easy comprehension. Massive bodies, enormous eyes, and total darkness. As we drift away from these giants, the ocean gently shifts focus again, because size is not the only way to survive here. Sometimes, success comes from cooperation. Coral reefs may look like stone cities beneath the sea, but they are built by billions of tiny living animals called coral polyps. Each polyp is no larger than a grain of rice. These animals secrete limestone skeletons, anchoring themselves to the seafloor. Over generations, the skeletons accumulate, forming vast reef structures that can stretch for hundreds of miles. Corals live in partnership with microscopic algae. The algae provide food through photosynthesis, while the coral offers protection and nutrients. This relationship gives reefs their vibrant colours. Despite covering less than 1% of the ocean floor, coral reefs support about a quarter of all marine species. Fish, crustaceans, mollusks, and countless others depend on them. Reefs grow slowly, often only millimetres per year. Their size reflects patience rather than speed. To swim above a reef is to float over centuries of quiet construction, tiny lives building monumental structures together. As we linger among these coral cities, another realization appears. Some reefs are so vast they can be seen from space, shimmering beneath the surface of Earth. Stretching along the coast of Australia, the Great Barrier Reef is the largest living structure on Earth. At over 1,400 miles long, it is so vast that astronauts can see it from space. What they see is not rock or land, but life. Billions of coral polyps, each building its tiny skeleton, have created an underwater landscape larger than many countries. The reef supports an extraordinary diversity of life. Fish flash in every colour. Sea turtles glide silently. Rays and sharks move through clear channels between coral walls. Despite its size, the reef is fragile. Changes in temperature, pollution, and acidification can disrupt the delicate balance between corals and their algae partners. When corals lose their algae, they turn pale in a process called bleaching. If conditions do not improve, entire reef sections can die. The Great Barrier Reef is both immense and vulnerable. A reminder that even the largest living systems depend on balance. As this idea settles, the ocean gently reminds us that life here is interconnected. From tiny algae to towering reefs, everything is linked, and those links extend into the water itself. Beneath shallow coastal waters, vast meadows of seagrass sway with the current. These underwater plants may appear modest, but they play a crucial role in Earth's systems. Seagrasses absorb carbon dioxide and release oxygen through photosynthesis. Per square metre, they can store more carbon than tropical rainforests, locking it into sediments for centuries. Their roots stabilise the seafloor, reducing erosion and protecting coastlines from storms. They also provide nurseries for young fish, seahorses and turtles, sheltering life during its most vulnerable stages. Seagrass meadows help keep water clear by trapping particles and filtering pollutants. Where they thrive, ecosystems are healthier and more resilient. Despite their importance, seagrasses are disappearing due to pollution, coastal development, and rising temperatures. Drifting above a seagrass meadow feels like floating over a hidden forest, quiet, productive, and essential. As the grasses wave below, the ocean feels less like a wilderness and more like a carefully balanced system. And within that system, some animals move between land and sea, blurring the boundary entirely. In certain coastal regions, the line between ocean and land becomes flexible. Mudskippers, small amphibious fish, can leave the water and move across muddy flats using their fins like limbs. They breathe through their skin and the lining of their mouths, allowing them to remain on land for hours at a time. Their eyes sit high on their heads, blinking as they survey their surroundings. Mudskippers climb rocks, defend territories, and even communicate through body movements. They live in a world where tides constantly redraw the boundary between sea and shore. Watching a mudskipper move feels like witnessing a moment from Earth's distant past, a reminder of the ancient transition from water to land. Other fish, like walking catfish, can also travel short distances across damp ground, especially during floods or droughts. These creatures show that evolution is not confined to neat categories. Life experiments continuously, exploring edges and in-between spaces. As the tide begins to rise again, the mud skipper returns to the water, and with that motion, our journey prepares to move onward, toward humanity's relationship with the sea, history beneath the waves, and mysteries still waiting. As the shoreline fades behind us, it's worth pausing to consider how little of the ocean we have truly seen. More humans have walked on the surface of the moon than have visited the deepest point in Earth's oceans. Since 1969, 12 people have stood on the moon. In contrast, only a handful have descended to Challenger Deep, the lowest known point in the Mariana Trench. It lies nearly 7 miles beneath the surface. The reason is not distance, but pressure. The deep ocean exerts a force so immense it would instantly crush an unprotected human body. Building vehicles capable of surviving those conditions is extraordinarily difficult. Space feels distant and hostile, yet the deep sea is often more extreme. Darkness, cold, and pressure combine into an environment that resists exploration. Despite advances in technology, more than 90% of the deep ocean remains unexplored. Vast landscapes and countless species lie unseen. This realization shifts perspective. Mystery is not only above us in the stars, it is beneath us as well. As we drift with that thought, the ocean becomes less familiar again, and within its depths, remnants of human journeys quietly rest, preserved by cold and time. Beneath the ocean's surface lies a vast archive of human history. It is estimated that more than 3 million shipwrecks rest on the seafloor, scattered across every ocean. Some ships sank in storms. Others were lost in battle. Many simply vanished, carried down by waves and time. Each wreck marks a moment when the sea reclaimed something built by human hands. Wooden vessels from ancient civilizations lie alongside steel ships from modern wars. Cargoes of pottery, tools, coins, and everyday objects remain where they fell, preserved beneath layers of sand and silence. Over time, many wrecks become artificial reefs. Coral grows across their hulls. Fish shelter inside broken timbers and metal frames. Life transforms ruins into habitats. Exploring a wreck is like stepping into a paused story. The ocean slows decay, especially in cold, deep water where oxygen is scarce. As we imagine these silent ships, the ocean feels like both guardian and keeper, holding memories without judgment. And some of these memories are astonishingly well preserved. In certain places, the sea acts not just as a grave, but as a vault, protecting history for centuries. In the coldest, darkest parts of the ocean, time moves differently. Low temperatures and lack of oxygen slow decay, allowing shipwrecks and artifacts to remain intact for centuries. In the Baltic Sea, a 16th century warship called the Vasa was recovered after more than 300 years underwater. Its wooden structure remained remarkably preserved, offering a detailed glimpse into the past. In the Black Sea, ancient Greek ships have been found with masts, ropes, and cargo still in place. These vessels sank into oxygen-poor depths where bacteria could not survive. The ocean, in these cases, becomes a natural museum. It holds history suspended, untouched by weather, fire, or human disturbance. Each preserved wreck tells a story not just of loss, but of survival. Objects meant for brief use endure far beyond their time. As we drift among these preserved moments, the boundary between past and present softens. The sea becomes a bridge across centuries, and beyond individual ships, the ocean holds something even larger. Entire cities once alive with people, now resting beneath the waves, waiting quietly in the dark. Not only ships, but entire cities now rest beneath the ocean's surface. Along coastlines shaped by earthquakes, erosion, and rising seas, human settlements have slowly disappeared underwater. Off the coast of Egypt lies the submerged city of Thonis Herakleion. Once a thriving port filled with temples and markets, it sank over 1,000 years ago. Statues and streets remain scattered across the seabed. In Greece, the ruins of Pavlopetri reveal a Bronze Age town more than 3,000 years old. Buildings, roads, and courtyards are still visible beneath shallow water. These submerged cities show how fragile human settlements can be. Shorelines shift. Land sinks. The sea advances patiently. Divers exploring these sites describe an eerie calm. Swimming through stone streets feels like drifting through a dream of history. The ocean does not erase everything. Sometimes it preserves. As these drowned cities settle into stillness, the sea reminds us that human time is brief compared to geological time. And beyond our structures and stories, the ocean holds mysteries that continue to inspire wonder, speculation, and legend. In the Western Atlantic lies a region long associated with mystery. The Bermuda Triangle, roughly bounded by Florida, Bermuda, and Puerto Rico, has captured the imagination for generations. Stories tell of ships and aircraft vanishing without explanation, compasses spinning, storms appearing suddenly, crews disappearing into legend. Many of these tales can be explained by natural causes. Strong currents like the Gulf Stream, unpredictable weather, heavy traffic, and human error all play roles in accidents at sea. Yet the mystery persists. The idea of an ocean region that resists understanding taps into a deeper fascination with the unknown. The Bermuda Triangle became less about facts and more about symbolism. It represents the ocean's refusal to be fully controlled or explained. Even with satellites and navigation systems, the sea remains powerful and unpredictable. As we let the myths drift by, the ocean feels vast again, a place where certainty fades at the horizon. And beneath that surface, unseen forces move water slowly across the planet. Currents so patient, they take centuries to complete their journey. Beneath surface waves and visible currents lies a slower movement. Deep ocean currents circulate water around the planet in a process that can take 1,000 years to complete. This global circulation begins when cold, salty water sinks near the poles. It flows along the ocean floor, eventually rising elsewhere as it warms and mixes. Each drop of water follows a long path, carrying heat, nutrients, and carbon across vast distances. The journey is slow, steady, and continuous. These deep currents help regulate Earth's climate. They store carbon in the deep ocean and distribute heat between hemispheres. Unlike surface currents driven by wind, these flows are guided by density and gravity. They move quietly, unnoticed by those above. To imagine a drop of water traveling for centuries is to imagine time moving at a planetary pace. As these deep currents continue their endless loop, the ocean feels less like a place and more like a living system, one that responds to cosmic forces as well, because the moon quietly overhead plays a constant role in shaping the sea. Twice each day, the ocean rises and falls in response to the moon's gravity. This movement creates tides, a rhythm as ancient as Earth itself. The moon pulls water toward it, creating a bulge on the side of Earth facing the moon. A second bulge forms on the opposite side due to inertia. As Earth rotates, coastlines pass through these bulges, experiencing high and low tides. The sun also influences tides. When the sun and moon align, their combined gravity creates stronger tides called spring tides. When they are at right angles, tides are weaker. Tides shape coastlines, nourish tidal ecosystems, and guide the behavior of countless marine organisms. Crabs, clams, and fish time their lives around this steady rise and fall. For humans, tides have guided navigation and fishing for thousands of years. Standing on a shore and watching the water advance or retreat is witnessing a cosmic connection. The pull of a distant celestial body shaping the movement of Earth's oceans. As the tide turns again, the ocean reminds us of its power, and sometimes that power rises higher than expected. A few times each year, tides rise higher than usual. These events are known as king tides. They occur when the sun, moon, and earth align in a way that amplifies gravitational pull. King tides can flood coastal streets, cover beaches, and push seawater farther inland than normal. They are natural events, but their effects are becoming more noticeable. As global sea levels rise, king tides offer a glimpse of the future. Places that flood briefly today may experience permanent inundation tomorrow. Communities around the world observe king tides to understand vulnerability and prepare for change. Photographs taken during these events help visualize what higher seas may mean. Despite their impact, king tides are quiet reminders rather than violent disasters. They arrive slowly, peak, and then retreat. Watching a king tide is watching the ocean reclaim space temporarily. It shows that the boundary between land and sea is never fixed. As the water recedes, the rhythm continues, and from this gentle rise and fall, we turn toward one of the ocean's most dramatic expressions of energy. Waves capable of crossing entire oceans at incredible speed. When an earthquake or landslide displaces a massive volume of water, a tsunami is born. Unlike wind-driven waves, tsunamis involve the movement of the entire water column. In the open ocean, tsunamis can travel at speeds exceeding 500 miles per hour, similar to a jet aircraft. Despite this speed, they may appear only as gentle swells far from land. As a tsunami approaches shallow water, it slows and grows taller. The energy compresses, turning a small wave into a towering wall of water. These waves can cross entire ocean basins in hours, affecting coastlines thousands of miles from their origin. Modern warning systems use seismographs, ocean buoys, and satellites to track tsunamis and provide alerts. Even so, their power remains humbling. Tsunamis remind us that the ocean is deeply connected to Earth's interior. Movement in rock becomes motion in water. As the sea settles again, calm returns, and within that calm, another powerful force waits, one that rises suddenly without warning, far from any earthquake. For centuries, sailors spoke of towering waves that appeared suddenly, rising from calm seas like liquid walls. These stories were once dismissed as exaggerations. Today we know rogue waves are real. Rogue waves form when smaller waves combine in just the right way, stacking energy into a single massive crest. They can be more than twice the height of surrounding waves. These waves appear without warning and vanish just as quickly. Ships encountering them describe being lifted abruptly, facing walls of water taller than buildings. Rogue waves can occur even during relatively calm conditions, making them especially dangerous. Modern instruments have confirmed their existence and measured their immense size. Despite scientific understanding, predicting rogue waves remains difficult. They are rare but unpredictable. Rogue waves remind us that the ocean is not entirely orderly. Beneath its rhythms lies chaos, capable of sudden expression. As the wave collapses and the sea smooths again, stillness returns. The ocean resumes its quiet breathing, and from this stillness, our journey will soon shift again, toward creatures, intelligence, and the subtle ways life adapts within this vast, restless water. As the surface settles after moments of chaos, the ocean returns to its true scale. Everything below about 200 meters, where sunlight fades away, is considered the deep sea. This vast realm makes up the largest habitat on Earth. It covers more than half the planet's surface and plunges miles downward. Forests, deserts, and grasslands combined occupy less living space than this hidden world beneath the waves. Within the deep sea live countless species, many still undiscovered. Creatures here are adapted to darkness, pressure, and scarcity. Some drift slowly, others glow softly. Many remain unseen by human eyes. Unlike land environments shaped by seasons and weather, the deep ocean is stable. Temperatures change little, currents move gently. Life unfolds at an unhurried pace. This stability allows unique ecosystems to persist for long periods, evolving slowly in isolation. Entire lineages exist nowhere else. To imagine the deep sea is to imagine Earth's greatest wilderness, vast, quiet, and largely untouched. As we drift through this immense habitat, another realization emerges. Life here is not only abundant, but incredibly varied. Some creatures have evolved senses beyond anything humans possess, allowing them to perceive the ocean in entirely different ways. In the ocean, vision is often limited. To survive, some animals rely on senses humans barely notice. Sharks and rays possess an extraordinary ability called electroreception. All living creatures produce tiny electrical signals as their muscles move and their hearts beat. Sharks can detect these signals through special organs called ampullae of Lorenzini located around their heads. This sense allows them to find prey hidden beneath sand or sediment, even in total darkness. A buried fish, invisible to the eye, becomes visible through its electric field. Electroreception also helps sharks navigate. Earth's magnetic field interacts with seawater, creating electrical cues that guide long-distance movement across open oceans. For sharks, the ocean is alive with signals we cannot feel. It is a landscape of energy as much as water. This ability turns the deep into a readable map, even when light is absent. As we imagine this invisible sense, the ocean feels richer and more complex. Reality here includes layers humans cannot perceive. And alongside these electric hunters, other animals communicate in different ways entirely. Some speak not through sound or sight, but through shared patterns passed down across generations. Culture is often thought of as uniquely human, but in the ocean, certain animals pass knowledge and behavior from one generation to the next. Whales and dolphins are among the clearest examples. Different groups of whales sing different songs. These songs change gradually over time and spread through populations, much like traditions. Young whales learn by listening, not by instinct alone. Orcas, also known as killer whales, show distinct cultures depending on their group. Some hunt fish, others specialize in seals. Their techniques are learned, not inherited. These cultural differences influence language, diet, and social structure. Two groups of the same species may live very different lives. This learning creates continuity beyond individual lifespans. Knowledge survives even as individuals come and go. In the ocean, culture is quiet. There are no written records, only memory, sound, and behavior. As this idea settles, the sea begins to feel less distant. Intelligence here is social, adaptive, and enduring. And within these social lives, cooperation becomes essential. Some animals depend on partnerships so close they cannot survive without one another.
In the ocean, survival is not always about competition. Many species depend on cooperation, forming partnerships that benefit both sides. One of the most familiar examples is the relationship between clownfish and sea anemones. Anemones are covered in stinging tentacles that repel most predators. Clownfish, however, are immune. The clownfish gains protection by living among the anemone's tentacles. In return, it cleans the anemone, brings it food, and chases away parasites. Other partnerships are equally important. Cleaner fish remove parasites from larger fish, even predators. Both benefit. One gets food, the other stays healthy. Some corals rely on algae for energy. Some shrimp rely on fish for shelter. These relationships create balance. Cooperation allows ecosystems to become more stable and resilient. When one partner disappears, the system can collapse. As we consider these alliances, the ocean feels less harsh. Life here is not only struggle, but connection. And within these connections, some animals develop extraordinary abilities to heal themselves, defying what we might consider permanent damage. In the ocean, injury does not always mean the end. Many marine animals possess remarkable regenerative abilities, allowing them to replace lost body parts over time. Starfish are among the most famous examples. If a starfish loses an arm, it can regrow it completely. In some cases, a single arm can regenerate into an entirely new individual. Sea cucumbers can eject internal organs when threatened, distracting predators. Later, they regrow those organs with little lasting harm. Certain fish can regenerate damaged fins. Some crustaceans regrow lost claws. Even corals can repair broken sections and continue growing. This ability allows survival in environments where encounters with predators are common. Regeneration turns damage into delay rather than disaster. The process is slow, guided by cellular signals that rebuild structure layer by layer. Watching a creature heal itself over time reveals nature's patience. Growth here is not rushed. As this quiet resilience settles in, the ocean feels forgiving, a place where loss is not always final. And beneath this resilience lies another quiet force shaping life, the chemistry of the ocean itself, influencing bodies in ways we are only beginning to understand. The ocean is not just water. It is a complex chemical environment that shapes how life grows, breathes, and survives. Salt content affects buoyancy and circulation. Dissolved gases like oxygen and carbon dioxide influence metabolism. Minerals support shells, skeletons, and cellular processes. Some organisms build calcium carbonate shells directly from seawater. Others rely on trace elements for enzyme function and growth. Changes in ocean chemistry can ripple through ecosystems. Slight shifts in acidity affect coral growth. Oxygen levels influence where animals can live. The ocean also stores vast amounts of carbon, acting as a buffer for Earth's climate. Much of the carbon absorbed by the atmosphere eventually dissolves into seawater. These chemical balances have existed for millions of years, finely tuned through time. As we consider this invisible influence, the ocean feels less like a backdrop and more like an active participant in life's story. Chemistry quietly guides survival here, unseen but essential. And from this invisible foundation, life rises into astonishing diversity. Some creatures grow so large or behave so strangely that they challenge our sense of what is possible. Despite centuries of exploration, the ocean still hides countless forms of life. Each year, scientists describe thousands of new marine species, from microscopic organisms to deep-sea fish. Some are discovered near the surface, hiding among coral reefs or coastal waters. Others are brought up from the deep by research vessels, strange and unfamiliar. Many new species look like something from science fiction: transparent bodies, glowing organs, unusual shapes adapted to darkness and pressure. Scientists believe that a large portion of ocean life remains undocumented. Estimates suggest that 2/3 of marine species may still be unknown. This means discovery is ongoing. The ocean is not a completed map, but a living frontier. Each new species adds another piece to the puzzle of how life adapts to extreme environments. As we drift with this idea, the ocean feels young again, full of possibility. And as long as mysteries remain, curiosity follows. Humans continue to search, listen, and learn, drawn by the same waters that shaped our earliest ancestors. Every human life traces back to the ocean. The earliest forms of life emerged in seawater billions of years ago, nourished by its chemistry. Even as life moved onto land, the ocean remained essential. It regulated climate, produced oxygen, and shaped ecosystems that allowed evolution to continue. Human history is tied to coastlines. Early settlements formed near the sea. Trade followed currents and winds. Cultures rose and fell along shores. Our bodies still carry signs of this connection. Salt in our blood mirrors seawater. Rhythms in our biology echo tides and cycles. The ocean feeds billions of people today, providing food, livelihoods, and connection across continents. Standing at the shore often brings a sense of calm or familiarity. Something ancient recognizes something ancient. As we reflect on this bond, the ocean feels less external, less distant. It becomes part of our story, not just our environment. And with that realization comes responsibility, because the ocean that shaped us is changing, responding to the choices humans now make on land. Today's ocean is not static. It is changing rapidly due to human influence. Rising temperatures, pollution, and acidification are altering marine environments worldwide. Warmer waters stress coral reefs, leading to bleaching events that can collapse entire ecosystems. Melting ice affects currents and sea levels. Plastic pollution drifts through even the deepest waters, entering food chains and accumulating in living bodies. Chemical runoff from land changes nutrient balances, sometimes creating oxygen-poor dead zones where few animals can survive. Despite these challenges, the ocean also shows resilience. Protected areas recover. Species adapt when given space and time. Scientists, conservationists, and communities work to understand and protect this vast system. As we acknowledge these changes, the ocean feels both fragile and powerful, capable of recovery, yet sensitive to imbalance. This awareness adds depth to our journey, because understanding leads naturally to reflection, and as the ocean continues to shift, it reminds us that mystery still remains. That much lies beyond our reach, waiting quietly in the deep. Even now, with satellites and submersibles, most of the ocean remains unexplored. Vast regions of the seafloor have never been seen by human eyes. Unknown species drift in darkness. Landscapes stretch beyond our maps. Processes unfold beyond our instruments. Scientists estimate that more than 95% of the ocean is still a mystery. Each expedition reveals something unexpected. The ocean reminds us that discovery is not finished. It is ongoing, quietly unfolding beneath familiar waves. Mystery does not only belong to distant galaxies, it exists beneath our own planet's surface. This realization invites humility. Knowledge has limits, wonder remains. As we float with this thought, the ocean becomes a place of rest rather than answers. A reminder that it is okay not to know everything. And with that calm acceptance, our journey begins to slow. We prepare to rise gently back toward reflection, toward meaning, and toward the final truth the sea offers us. When people think of Earth's oxygen, forests often come to mind. But most of the oxygen we breathe comes from the ocean. Tiny organisms called phytoplankton drift through sunlit surface waters, quietly shaping the atmosphere. Through photosynthesis, phytoplankton use sunlight to convert carbon dioxide into energy. In the process, they release oxygen. Collectively, they produce more than half of Earth's breathable oxygen. These organisms are microscopic, yet their impact is global. Vast blooms can stretch for miles, visible from space as green and turquoise swirls across the sea. Phytoplankton also form the foundation of marine food webs. From the smallest zooplankton to the largest whales, countless lives depend on them. Their populations shift with seasons, currents, and temperature. When conditions change, their influence ripples through ecosystems and climate alike. Every breath carries a trace of their work, a quiet gift from the sea delivered invisibly through air. As this realization settles, the boundary between ocean and human fades again. The sea is not distant, it is inside us, and with that intimacy comes scale. Because the ocean does not merely support life, it dwarfs the land itself. The Pacific Ocean stretches so wide that it defies intuition. Covering more than 60 million square miles, it is larger than all of Earth's continents combined. If you were to sail across its widest point, the journey could take weeks even at modern speeds. Entire island chains exist in isolation, separated by thousands of miles of open water. Within the Pacific lie the deepest trenches, the largest volcanoes, and some of the most remote ecosystems on the planet. Storms form and fade without ever touching land. For centuries, this vastness shaped human history. It isolated civilizations, delayed exploration, and inspired myths of endless water. Even today, much of the Pacific remains sparsely traveled. Its scale resists control and comprehension. From space, the Pacific dominates Earth's appearance. The planet looks blue not because of land, but because of water. As we drift across this immensity, the ocean feels less like a feature and more like the defining presence of Earth itself. And this presence has shaped not only geography, but time. Oceans open and close. Continents drift. Nothing remains fixed forever. Oceans may feel permanent, but on geological timescales, they are temporary. Earth's surface is constantly reshaped by tectonic forces beneath the sea. Hundreds of millions of years ago, a single vast ocean surrounded the supercontinent Pangaea. As continents split apart, new oceans formed in widening rifts. The Atlantic Ocean is still growing today, slowly expanding as tectonic plates drift apart. In contrast, the Pacific is shrinking as plates slide beneath surrounding continents. Over time, oceans close, seafloor sinks into the mantle, water relocates, new basins open elsewhere. This slow cycle, known as the Wilson cycle, repeats over hundreds of millions of years. Oceans are born, mature, and vanish. What feels eternal to humans is momentary to the planet. As we imagine oceans coming and going, Earth feels alive, breathing slowly across ages far beyond memory. And within this immense timeline, life adapts again and again. From the first cells in ancient seas to modern ecosystems, the ocean remains the stage. Which brings us gently toward reflection, because the ocean is not only history, it is origin. All life on Earth traces its roots to the ocean. Billions of years ago, the first living cells emerged in seawater, nourished by chemistry and energy. These early organisms found protection and stability in the sea. Water buffered temperature swings and provided the ingredients needed for life to persist. Over time, complexity grew. Cells formed communities. New metabolisms emerged. Eventually, Some life ventured onto land, carrying the ocean within it. Even now, every living body reflects that origin. Salt concentrations in human blood resemble ancient seas. Our earliest development unfolds in fluid environments. The ocean is not just where life began, it is where life learned to survive. As we reflect on this, the sea feels familiar in a deep, quiet way, less like an external force and more like a shared ancestor. Standing at the shore is standing near the beginning, and while the past flows behind us, the future flows ahead. Because the ocean does not only hold history, it holds possibilities yet unseen. The discovery of life thriving without sunlight transformed how scientists think about the universe. Deep-sea ecosystems powered by chemistry suggest that life does not require Earth-like conditions. Icy moons such as Europa and Enceladus are believed to have oceans beneath their frozen surfaces. Heat from their interiors may drive chemical reactions similar to those on Earth's seafloor. If life can exist in darkness, pressure and cold here, it may exist elsewhere too. The ocean becomes a model for astrobiology. Studying its depths helps scientists imagine life beyond our planet. Every vent community and extremophile expands the definition of habitability. As we consider this, the ocean feels like a bridge between worlds, a reminder that Earth is not isolated in possibility. Looking into the deep is like looking into the cosmos. Both invite wonder. Both resist certainty. And as our thoughts drift outward, they also drift inward. Because exploration is not only about discovery, it is about perspective. The ocean humbles by its size, depth, and patience. It reminds us that human timelines are brief compared to planetary rhythms. Waves erase footprints within hours. Currents move continents over millions of years. Life adapts slowly, quietly, persistently. In the ocean, dominance is temporary. Balance is everything. Excess disrupts systems that took ages to form. This scale invites humility, not insignificance, but perspective, a sense of belonging within something far larger. Standing before the sea often brings calm because it places worries into context. The ocean does not rush, it does not argue, it simply exists. As we drift with this feeling, the ocean becomes less something to conquer and more something to listen to. And listening brings stillness, awareness, rest, which leads naturally toward the final truths of our journey. Because beyond facts and figures, the ocean offers something quieter. Beneath all its power, the ocean is rhythmic. Waves rise and fall, tides advance and retreat, currents circulate endlessly. These patterns repeat with comforting consistency. Day follows night, high tide follows low, motion returns to stillness. Life in the ocean is shaped by these rhythms. Creatures time-feeding, migration, and rest to predictable cycles. Even storms follow patterns, forming and dissolving within larger systems. These rhythms extend beyond water. Human bodies respond to repetition. Breath slows, heartbeats settle. Listening to the ocean often induces calm because it mirrors internal rhythms we recognize instinctively. As our attention softens, the ocean feels less overwhelming. Its vastness becomes soothing rather than intimidating. Rhythm replaces urgency, and with rhythm comes rest. The mind begins to release its grip, which brings us gently toward closure, not an ending, but a settling, a quiet return. Every continent is touched by the ocean. Every climate is shaped by it. Even each breath carries a quiet trace of the sea. Water rises from the surface as vapor, drifts through the sky, falls as rain, feeds rivers, and returns again. This cycle never truly ends. It simply changes form. Life is woven into that movement. From microscopic plankton to forests and cities on land, the ocean's influence stretches far beyond its shores. What happens in the sea never stays contained. Currents link distant places without borders. Warm water travels from the tropics toward colder coasts. Nutrients drift across entire basins. Energy moves slowly, patiently, connecting places that may never meet directly. These pathways remind us that separation is often an illusion. Systems overlap, effects linger, motion continues long after the surface appears calm. The ocean does not rush. It carries the past forward, holding traces of what has been, even as new moments unfold above it. And as the body settles and the mind grows quiet, we can begin to sense this deeper rhythm. Because before the ocean shapes the future, it remembers the past. And that brings us gently to the next truth it holds. The ocean does more than move water across the planet. It remembers. Every current, every layer, and every slow circulation pattern carries a record of past conditions. Long after the air above has changed, the ocean continues to hold traces of earlier climates within its depths. Water moves slowly. Some deep currents take hundreds or even thousands of years to complete a single journey around the globe. Along the way, they transport heat, carbon, and nutrients, quietly preserving the state of the planet at the time they formed. Scientists study deep ocean temperatures and chemical signatures to understand Earth's past. These hidden records reveal ice ages, warming periods, and shifts in atmospheric composition that happened long before humans kept measurements. Because the ocean responds gradually, it smooths sudden changes. It slows extremes, spreads energy, and cushions the planet against abrupt shifts. This steady pace gives Earth a kind of memory, one written not in books or data, but in water itself. Yet this memory also means change lingers. What enters the ocean does not disappear quickly. Energy absorbed today may remain long after the surface has moved on. And that leads us gently to the ocean's next role. Not as a witness of change, but as its greatest reservoir. The ocean plays a crucial role in regulating Earth's temperature by absorbing and storing heat. More than 90% of the excess heat generated by greenhouse gas emissions is absorbed by the ocean rather than the atmosphere. Water has a high heat capacity, meaning it can take in large amounts of energy without warming quickly. This property allows the ocean to act as a thermal buffer, slowing rapid changes in global climate. Heat absorbed near the surface is gradually transported by currents into deeper layers, where it can remain stored for decades or even centuries. This redistribution helps moderate temperatures on land, reducing extreme swings between hot and cold. Without the ocean's ability to absorb heat, Earth's surface would warm far more quickly, making conditions much harsher for life. However, this heat storage has consequences. As ocean temperatures rise, marine ecosystems experience stress. Coral reefs are especially sensitive, and warming waters can disrupt species distributions. The ocean's role as a heat reservoir highlights its importance to planetary stability. It quietly balances energy, absorbing change that would otherwise be immediate and severe. As this fact settles, the ocean reveals itself once more as Earth's great stabilizer, vast, patient, and deeply influential. As you rest now, imagine yourself floating gently, supported, weightless, nothing required of you. The ocean holds you without effort. Your breath slows like waves on a quiet shore. Thoughts drift like clouds over open water. There is nowhere else to be. The sea has always been here. It will continue long after this moment. For now, let it carry you. Let curiosity fade into calm. Let the deep settle into silence. Good night.